We're going to look at one more application of exponential growth decay type formulas here, and that's with Newton's law of cooling. So what this says, what this law says, is the rate of cooling of an object is proportional to the temperature difference between the object and its surroundings, provided that this difference is not too large. So we're talking, lower temperatures here, nothing too extreme. So the way to model this law is with this differential equation right here. So the rate of cooling, that's the derivative. This is our rate of cooling. And this T minus T of S, this is our temperature difference. So capital T is the temperature of our object, and capital TS, that's the constant temperature of our surroundings. So we're going to assume that our surrounding temperature is going to be constant for this discussion. And so what Newton's law of cooling says is this rate of cooling, this derivative, the change in the temperature of our object over time, is proportional to the temperature difference. So the temperature of our object minus the surrounding temperature. And K here is our constant of proportionality. All right. So that's Newton's law of cooling. So we've taken this kind of word, this phrase here, this expression, this paragraph, and we've written it as a differential equation. Now it turns out the solution for this differential equation is very similar to our exponential growth and decay formulas. So it's going to involve this e raised to the k times t. And it turns out it's equal to, the formula for our temperature of our object is equal to its initial temperature minus the surrounding temperature times this exponential term, and then plus the surrounding temperature. So it's not quite the same formula. There's a little bit more going on here because we're adjusting here by the surrounding temperature. But it's a very similar looking equation. And so let's just kind of write out what some of these gadgets are. So the function T of capital T here represents the temperature of our object that's cooling down. T sub S is the surrounding temperature. Usually this is like air temperature. So this is the surrounding temperature, and we're assuming that it's constant. So for our discussion here, the surrounding temperature is being held constant. It's not changing over time. The only thing that's cooling down, the only thing that's undergoing a temperature change for this discussion is the object. And T0 is just the starting temperature. All right, so we have these three gadgets. We have our function capital T, which is the temperature function. We have capital TS, which is just the constant surrounding temperature. And then we have T0, which is the starting temp of our object. And so we can use Newton's law of cooling. We can use this differential equation and the resulting function to, answer some questions about an object that's undergoing cooling. So let's take a look at an example. Let's suppose that we have a beverage that's at room temperature. So we have this drink, and it's at a room temperature of 72 degrees Fahrenheit, and we place it in a refrigerator where the temperature is a constant 44 degrees Fahrenheit. And what's going to happen is this drink that we put in there is going to cool down. And so what we want to do is we want to find a function capital T that describes the temperature of our drink at time t. So for this object that's undergoing a cooling, let's write down our temperature function. It's going to be the starting temperature minus the surrounding temperature times this e raised to the k times t, and then plus the surrounding temperature. All right, so let's think about what we need to, what information we're given, and then what we need to find to really answer this question. So a beverage that starts off at room temperature. So this 72 degrees Fahrenheit, this is the starting temperature of our object. So that's really telling us our starting temperature is 72. Well, we're placing it into a refrigerator with a constant temperature of 44. So 44 is going to be our surrounding temperature. And then we're given this additional information here that after half an hour, the temperature has cooled to 61 degrees Fahrenheit. So let's write that out. Half an hour, it has cooled to 61 degrees Fahrenheit. So we have some choice here about the units for time that we want to use. Do we want to use minutes or do we want to use hours? Or we could use seconds. We have choices. Since we're given in terms of hours here, let's just kind of stick with the hours. So what this is saying is that our temperature after half an hour, so our temperature at 0.5 hours, should be 61. And we're going to use these three pieces here to find our temperature function. And we can see the initial temperature is going to fill in right here. Our surrounding air temp is going to fill in here and here. And then we need to use this information to help us find this constant K. All right. So let's see how this is going to work. So that's what we need to do. We need to determine K. And the way we're going to do this is we're going to work with this equation and work with this equation. So let's fill in these two pieces that we already know. Let's put them in here. So that's going to give us an updated temperature function here. So the starting temp minus the surrounding temp here, let's calculate that difference. So 72 minus 44 is what? 28. So we're going to have 28. So that's the starting difference here. Then times our exponential function, e raised to the k times t. And then plus our surrounding temp, which is 44. All right, so this is our temperature function so far with these two pieces filled in. And now we want to use this extra information that we know. We've taken a measurement here that after when we plug in 0.5 into this equation, we should get 61. So let's actually do that. we know that when we plug 65 in, let's see what happens when we actually plug 0.5 into this equation. So we're going to get 28 e raised to the k times 0.5 plus 44. And doing this, we should get out 61. So we've plugged 0.5 into here, and we know we should be getting out 61. So this gives us an equation then that we can then use to find k. And this is going to be very similar to the ones we've been doing, solving this exponential function. First thing we want to do, though, is kind of move this 44 over to the other side. So that'd give us 28 e raised to the k times 0.5 is equal to, what's 61 minus 44? What is that? 17? Yep. All right. Now we want to get this exponential term all by itself. So next thing we want to do is divide both sides by 28. So that's going to give us e all by itself there on the left. So e raised to the k times 0.5 is equal to 17 over 28. Next, we want to get rid of that e. So we're just kind of working our way through this left-hand side. First thing we had to do was get rid of this 44, move it over. Then we had to get rid of this 28, divide it over. Now we want to get rid of the exponential, the e. And the way we do that is with our natural log function. So we're going to apply natural log to both sides. And when we do that on the left, the natural log and the e just cancel. And that gives us k times 0.5 is equal to natural log 17 over 28. And then finally, finish solving for k. So divide by 0.5. So k is equal to, this is 1/2. So this is going to be natural log 17 divided by 28 all over 0.5. And if you were to calculate this out, what you would see is natural log of 17 over 28 is negative. So this constant k is negative. And, you know, when we have a negative exponent for this exponential function, what's happening is it's undergoing some sort of decay. And that agrees with our interpretation here that the temperature is cooling down. The temperature is kind of decaying. All right, so this is our k value. Now let's actually plug it in to get our nice temperature function. So we're going to have 28e raised to the natural log of 17 divided by 28 all over 0.5 times t, and then plus 44. So there's our nice temperature function now. That describes the temperature of our beverage that's sitting there in the fridge. So we can kind of model the temperature for that object that's undergoing some cooling. So we can answer then all sorts of questions based off of this function. So let's look at the next part. What is the temperature after another half an hour goes by? Well, if one half an hour went by and then another half an hour goes by, what this is really saying is, what's the temperature after 1 hour? So just plug 1 into the function. So if we plug 1 into the function that we just found, let's go back. What do we find? Here it is. We're plugging 1 in for t. So it's just going to be 28e raised to the natural log 17 over 28 divided by 0.5 times 1. So really we won't write the times 1 plus 44. I did write the 1. Plus 44. And if we were to calculate this out, It's approximately 54.3, and the units here are degrees Fahrenheit. So that's our temperature of our object that's cooling down in the fridge after 1 hour. All right. Well, we see that after 1 hour, it's at about 54.3 degrees Fahrenheit. And we might be interested in knowing, well, how long does it take for the drink to cool down to 50 degrees Fahrenheit? So the idea here is we want to know, when is our temperature equal to 50? When is the temperature of our object equal to 50? So we're going to set our temperature function equal to 50 and then solve for t. So let's take our temperature function. What was it? It was 28 e raised to the natural log 17 over 28 divided by 0.5 times t plus 44. And we're going to set this whole thing, this whole temperature function here, equal to 50. And what we want to do is we want to solve for the time. So again, we're just kind of unraveling this equation. The t here is in the exponent of our exponential function. So we just want to move all the other terms to the other side. So we're going to start with this plus 44, move it over. So subtract 44 from both sides. And then that gives us 28 e to the, and I'm going to, just to save on writing, I'm just going to keep this a k. So I'm going to keep that a k times t. We know what k is. We've already found it. But just to kind of save on the writing here, we'll write it as k times t. And 50 minus 44 is, what is that? 6. Now we're trying to solve for t. We already know what k is. So now we want to get rid of this 28. So divide both sides by it. So when we do that, we get e raised to the k times t is equal to 6 divided by 28. And now we want to get rid of the exponential part here, so apply the natural log function to both sides. Didn't quite leave enough space there. We'll jam it in. Natural log and e, once they're right next to each other, cancel out. And so we're left with k times t is equal to natural log 6 divided by 28. And then finally, we want to solve for t, so divide both sides by k. And that gives us our value for t. T is equal to natural log 6 divided by 28 divided by, and let's fill what k actually is in. We actually know what k is, so let's fill that in. K was natural log 17 over 28 divided by 0.5. So if we're dividing by k, it's just going to be the reciprocal. So it'll be natural log 17 over 28, and then we'll put our 0.5 up top. And so there is the exact time the object will be at 50 degrees Fahrenheit based on this function. And if we were to calculate this out just to kind of conceptually see when this would be, it's approximately, let's do our approximation here, get our decimal approximation. This is about 1.5 hours, 1.544, and the units here are hours. So we made that choice when we first started figuring out our temperature function here and the value for k. We made that choice to use 0.5, which was in terms of hours. And so that means our time value is in terms of hours. If we had used 30 minutes, perfectly fine to do that, 30 minutes, but then this t value, whatever we would have gotten, would have been in terms of minutes instead. So we would have gotten, the numbers would be slightly different. This would be, about 90 minutes or so if we had found this K value in terms of minutes. But this is in terms of hours. So the units for our function here are in terms of hours. All right. Or for our time here is in terms of hours. So you can kind of use this function then, use this model of our cooling drink, use this function to, essentially make predictions, make estimates for when it'll reach certain degrees, or when it'll reach certain temperatures. All right, so that's going to do it for exponential growth and decay. So we saw we can use that to model population growth of a population of organisms that are experiencing growth. We can use it to model decay, so radioactive decay. We can also use it to model cooling as well. Lots of applications here. All right, so that's going to do it. And nice fun application here to kind of end things off. And we'll see what we do next. Bye-bye.